In this video, we are going to solve a problem on carbohydrate and stereochemistry. They are given 4 compounds in Fischer projection. All are basically carbohydrate. About that, they are given some statements. They are given 5 statements P, Q or S, T. Among these, which are true? I have taken this problem. The reason it involves so many basic concepts. The first statement, 1 and 2 are diastereomer. So you should know what do you mean by diastereomer. What will be the difference for diastereomer in Fischer projection. Second one, first and fourth are mesomers. So you should know what do you mean by mesomers. And will it be optically active? Next one, first and third can be interconverted by a base. This statement involves a basic concept of enolization. The next one, only 1 and 4 are cleaved by HiO4, periodic acid. We'll see that. Last one, first and third are D sugars, second and fourth are L sugars. You should know so many basic concepts about the stereochemistry and carbohydrate. First, let us go for diastereomers. What do you mean by diastereomer? When you go for more than one chiral center, the number of stereoisomers will be more. If you go for 2 chiral centers, there will be 4 stereoisomers. So, we needed some shortcut, some terminology to express what is the relationship between the stereoisomers. So that is basically enantiomers and diastereomers. Diastereomers are stereoisomers which are not mirror images. It is possible only when there are more than one chiral centers. If there is only one chiral center, there won't be diastereomer. Enantiomers are mirror images. For any diastereomer, there will be one enantiomer. You can take any stereoisomer, there will be its mirror image, that is enantiomer. So for a stereoisomer, there can be only one enantiomer, whatever may be the number of chiral center. For a particular stereoisomer, there will be only one enantiomer. But diastereomers are not like that. Depending on the number of carbon, it will increase. When you go for Fischer projection, take this compound. If you go for the mirror image of this, so these 2 are mirror images. OH is here, afterwards we come across carbon, it is here, hydrogen, CHO on the top, CHOH at the bottom. So these 2 are mirror images, so they are enantiomers. Suppose if I go for 2 chiral carbons, then the mirror image will be like this. So these 2 are enantiomer. Like this, for any stereoisomer, you can go for the mirror image, that will be the enantiomer. On the other hand, if you go for this, the OH is here, so that is mirror image, but here I have OH, this side it is hydrogen. So this is not the mirror image of this molecule. So these are called diastereomer. Now let us try to apply the concept and let us check whether the first statement is it correct or not. 1 and 2 are diastereomers. Look at this, 1 and 2, they are diastereomers. They are not mirror images. If they are mirror images, then here we should get OH, but it is not there. So this statement is correct. Second and third are enantiomers. You can see here OH, OH, CH3, CH3, CH2OH, CH2OH, CHO, CHO. Second and third are enantiomers, so that is correct. So statement P is a true statement. I can eliminate the given options which do not have P. If you see the first one, there is no P, so this is wrong. If you go for the third one, there is no P, so I can eliminate this. The second one, if Q is correct, then I can go for this option. If Q is wrong, then I can eliminate this option. This will be the answer. I need not go through all the statements. The second statement itself I can conclude. First and fourth compounds are mesomers. Are they mesomers? And are optically inactive. When you go for mesomers, they will have plane of symmetry. Let us take this molecule. Instead of this molecule, if they had given this molecule, then it has plane of symmetry. So you can see here, this portion will be mirror image of this. If I keep the mirror plane here, OH will be here, CH2OH, hydrogen and nitrogen. But in this case, we have CHO, not CH2OH. Even though these two are mirror images, we don't get mirror image here. Because of that, they are not mesomers. And are optically inactive? No, it is optically active. It has two chiral centers. For both the chiral center, the rotation will be different. So this statement is wrong. So I can eliminate this. P, R and T are correct. Now I can cross check whether R and T are correct or not. Suppose if you take an aldehyde like this, which has hydrogen. If you add a base to this, base can abstract this proton because it is acidic. After that, what we get is minus charge. I should not draw like this, but still that becomes enolate. Now when it comes back, it can take hydrogen from the top as well as from the bottom. Because of that, the chiral center is destroyed. Finally, the product, whatever you get, will be a racemic mixture of these two compounds. Here, the R1, say it is CH3, it may become thin line as well as thick line because the chiral center is destroyed. For that, there should be alpha hydrogen. If there is no alpha hydrogen, that is not possible. In the problem, they are given CH3. It is not hydrogen, it is CH3. I think it is a mistake. It should be hydrogen. Then only they are interconvertible. If you add base, it will get converted into the another one. This should be hydrogen, not methyl. Then only this statement is correct. The last statement, first and third are D sugars, second and fourth are L sugars. That is correct. How do we give the nomenclature? as D and L. From the bottom, we go for the carbons. This is the first chiral carbon. In that, if OH is attached towards your right hand side, that is D sugar. If it is attached towards your left hand side, that is L sugar. You can see here, first and third, the OH, it is towards your right. Third and fourth, it is towards left. So this D, L, D, L. So this statement is correct. P is correct, but or it is correct only if you have hydrogen in the place of methyl. There is mistake in the question. If it is methyl, it cannot get interconverted.